Okay, so here was the deal with the inclined plane. We have a mass m on a frictionless incline that's tilted at an angle theta. Just to quickly recap what happened in this problem, what we found was that there are two forces, force of gravity and normal force, that are relevant. We found that the normal force killed not all, but some of the force of gravity. The part of force of gravity that was, the part of the force of gravity that was going to potentially violate the structural integrity of the surface. So these two forces cancel, and then the leftover component of the force of gravity, which is mg sine theta, is what actually is the net force. Come in like this if you come in. So the leftover part of the force of gravity, that's basically is the net force. If these two kill each other, then this is all that's left. That's the net force. That causes the acceleration. And so since the normal force canceled mg cosine theta, then the net force is mg sine theta. That causes an acceleration of g sine theta. So those were basically the results that we got. And what I want to show you now is a method of verifying that we did it correctly. So this is called checking your limits. So this is a way of error checking answers when error checking solutions. So you can error check solutions when they are symbolic. So here's how it works. I made the point before that when you solve something symbolically, it's a very powerful answer, because I haven't just done this problem for any old theta. I haven't done it only for 30 degrees or 22 degrees. I've done it for any theta. You could just plug into those any angle you wanted. What we're going to do is we're going to leverage that, and we're going to say, if we have actually solved this problem for any theta, there are certain special thetas. These are called the quote-unquote limits, because usually there are these extreme cases. There are certain thetas where we know exactly what should happen. Probably you can't intuitively say, I know exactly what should happen at 21.7 degrees. That's not a limit. What would be some angles, though, where you kind of know what's going to happen? What angles of incline? 0. 0 degrees is not an incline anymore. It's flat. So the first limit I'm going to explore is theta equals 0. So I'm going to redraw it with an incline with a vanishingly small angle until there's no tilt at all. It looks like this. So let's check our intuition. How big do you expect the normal force to be right there? Not quite. Remember, normal force is going to have to cancel the force of gravity, not the acceleration, right? What is it? mg, yes. So by intuition, we have that the entire force of gravity, which is mg, also known as the weight, is now going to be acting into the surface, and the surface says, no way. Okay? So the surface is entirely going to say, no way. And then by our intuition, how much is something going to spontaneously accelerate in the x direction on a flat surface? 0. It's not going to go anywhere, right? It's not going to slide by itself on a flat surface. And the reason why, of course, is because now the normal force has a bone to pick with the entire force of gravity. Over here, it just didn't like this component, right? But this component was parallel to the surface, and the surface has no problem with that. There's friction, which we'll introduce later, but that's a different story. So we went from the normal force just killing a part of the force of gravity to killing all of it, because all of it is acting into the surface, right? So this is just our intuition, what should happen, and we can now plug in theta equals 0 into our general equations, our symbolic solutions, and make sure that they produce these, because if they don't, there's a problem with them. So now let's check our equations. So mg cosine theta is our equation for normal force, and g sine theta was our expression for acceleration. What's cosine of 0? 1. Does it check out? Yep, that's exactly what we expected. What's sine of 0? 0. So the acceleration is 0. Does that check out? Yes, it does. So we figure out real quick if we messed up the SOHCAHTOA when we're assigning our gravitational components, right? If we accidentally had the cosines and sines reversed, there'd be a huge red flag because it wouldn't work. We would not get the answers that we know from common sense we should be getting, okay? Now, that's no guarantee that there could not be any error possible, okay? But whatever error might be in there has at least evaded detection for this particular limit. There's another limit we could try too. Let's try that other one. What is another angle where we kind of know exactly what should happen? 90. So we have an incline which is so steep that it is approaching vertical. In fact, it is vertical. Let's draw that. This is going to look a little weird. Most people wouldn't characterize that as an incline, but it is. So our theta here has approached 90 degrees. And as strange as it may seem, our axes, of course, were chosen so that x is downhill and y is perpendicularly outward. So now those are going to tilt in the kind of a weirdest way. They're going to look like this. X is down, not just no longer downhill, but just down. And then y is actually to the right. So let's check it by our intuition again. What should happen to these accelerations? And make sure our equations match. How much normal force is needed here to prevent the surface from getting smushed? 0. You have no danger whatsoever of the surface being smushed in this case. The force of gravity is entirely parallel to the surface. There is not all of it, not even some of it is even into the surface now, right? Surface has no problem with that whatsoever. Why would the surface need to push on the object when the object's not pushing into it? You hopefully believe me if you drop something next to a wall, right? The wall is basically isn't doing anything, right? It's just free falling next to a wall. What acceleration do we expect? Is it minus or plus g? G itself is amount, and is the direction positive or negative? Positive, yeah, because plus is downward now. You can see why there's never, ever, 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 ever a negative in the g itself, because you don't want it in there. You put the sign in the front depending on the situation. In this case, the acceleration is downward, yes, but downward is positive. And the amount, g, is always 9.8 meters per second squared. The negative is never in there because you don't always want it in there, okay? In this case, it's positive because of your axis choice. So we can go ahead and plug in, again, check it against our solutions. N equals mg cosine of 90. Cosine of 90 is 0, so this checks out. And over here, the acceleration is plus g sine of 90. Sine of 90 is 1, so that checks out. So if there is an error in our expressions, it is hiding out incredibly stealthily. And I'm here to tell you that, of course, there isn't, okay? So checking limits can really help you kind of sleuth out if there's a problem, especially for SOHCAHTOA. If you mixed up your sines and cosines, it'll come out really quickly. If you check your answers, your symbolic answers, against some sensible real-world head check, right? That's what checking your limits is. Are there any questions so far? Okay, so this actually affords me the opportunity also to do kind of a generalized survey of what the results are for an inclined plane. For an inclined plane, we might want to kind of summarize, as you go from 0 to 90, your angle of your incline is increasing. What happens to the various quantities? Of course, a 0-degree incline is completely flat, and a 90-degree incline is completely a vertical wall. Okay? So here's what we found. The normal force, so I guess I label here what variable I'm talking about. The normal force went from, when you're flat, the normal force completely cancels out the entire force of gravity. And therefore, how much acceleration do you have? Nothing. There's nothing left over. Right? So that's what we found here, right? The normal force and gravity kill each other. That's the end of the story. Nothing happens because there's nothing left over to make it happen. By the time we have gone to a vertical wall, the normal force is completely turned off. It's actually decreasing. The general expression, if you want it at any angle in between, is mg cos theta. It's decreasing because it's less and less pissed off at the force of gravity, right? It has less and less a problem with what the force of gravity wants to accomplish, right? If it's a flat surface, it hates the force of gravity. If it's a vertical surface, it doesn't mind gravity at all because it's not trying to smush the surface. And as the force, the normal force starts to cancel less and less of the force of gravity, gravity is more and more free to do its thing. And by the time we get to a vertical wall, we of course are in free fall. We're in free fall next to the wall. So the acceleration, which is speaking to how much of the force of gravity is actually left over and not killed, if you want to do it in between, is g sine theta. So that's kind of a summary of the results of what happens on an inclined plane. The inclined plane is basically the hybrid between a flat surface where nothing happens and a vertical surface where you have an object in free fall. In fact, the very first measurements of g, the gravitational acceleration, were not made the way you did it in lab, where you had that crazy electrical apparatus with the high voltage, okay, that went off every 1/30th of a second. Remember that thing? Okay. They didn't have those back, in the 1500s, 1600s. Okay. It has to be something quick, because how long does something spend falling? Like less than a second, right? So you need very precise machinery in order to figure out what is going on when. So instead, what Galileo originally did, he used for his timing, he used this pulse. Not very accurate, right? And so he had to do it on a very, very small, low incline, right? So the thing would take long enough to go down, right, so that he could actually time it. So he wasn't really measuring g, he was measuring g sine theta and then dividing out the sine theta. Okay? Now if you ask where did he get a frictionless inclined plane? Well, of course, they don't exist. His results were actually full of errors. Okay? But the fact that he actually even thought of doing it, okay, back in the day was a monumental achievement. Okay? Question?
What did he get?
For the value?
Yeah.
I don't actually know the exact result. I think he was off because what he actually did was he rolled things down, and it turns out we'll learn like around homework 10, if you roll something, there's actually a factor introduced into the acceleration, and this factor can be actually significantly different from 1. So he didn't have enough sophistication to be able to know that, of course, at the time. This was before Newton's time, so a lot of this stuff that we're talking about wasn't known at all. Okay, so that's a summary of an inclined plane. Just one kind of popular interest thing that I might mention, how this might apply to real life. If you ever been watching TV or something like that and you see like a skier or a snowboarder and they jump off a cliff that is like 100 feet tall, and you wonder, how did they just not break their legs doing that? Now, the soft snow is obviously a lot to do with it, but I definitely don't recommend, no matter how soft the snow is, to jump off a 100-foot cliff. There's a thing there that may not be obvious on television what's going on. They're falling off some big cliff onto a slope which is basically extremely steep. And especially with snow, you can't really tell. So if you think about what's going on here, I'm not going to try to draw, well, I guess I'll try. So here's a snowboarder, okay? So if they're falling, their acceleration, of course, is g, and just magnitude. And if you go from basically a vertical fall to a very steep slope, then you're basically only a shade off from continuing to free fall, right? So if you're here, I guess I'll try to draw them like that, the force of gravity is extremely close to being parallel with the slope, right? You have only a very small component that's offensive to the force of gravity. You have most of this is still parallel to the surface, right? And so the normal force, which is what actually is going to hurt you, right? As they say, it's not the fall that kills you, it's the sudden stop, right? The actual normal force that is necessary to cancel off that component is relatively small. In fact, if you carefully watch, you'll notice a lot of times when they land, they actually continue to speed up, okay? And the reason, again, is because when you are on a very steep incline, most of the force of gravity is parallel to the surface, and only a small component of it is offensive to the normal force, and the ground comes in and cancels it. Does that make sense? Okay, so that's it for, again, we finished the kind of the meat and potatoes of the problem last time, but I wanted to talk about the inclined plane in a little bit more detail, because it does come up that we want to, in the class, look at motions that are on a tilted surface, right? It's obviously a very common motion in the real world. The next order of business that I want to talk about, any questions before I move forward? Okay, so then let's talk about that elevator problem that's on your homework. This is going to be a discussion of apparent weight and weightlessness. So let's talk about first, when you get on a bathroom scale, what is it that's happening? What is it that you are actually doing when you are, quote unquote, and I do emphasize the quotes, weighing yourself? So this is a problem where the first step of the problem-solving strategy may not seem so trivial. The first step of that 6-step plan that I introduced last time, identify the object of interest. So are we interested in the person or the scale or the earth? What are we going to focus in on? And I would suggest that we focus in on the person. So the person is our object of interest, and they are going to experience, what is the force that they'll experience? Force of gravity, that's one. And then there's one more. Normal force from the surface, right? Because the surface that they're standing on, in this case, the scale, does not want to get smushed. So there'll be a normal force. And just for the purposes of identifying what's happening, I'm going to say that, of course, the force of pull of the force of gravity comes from the earth. That's what's pulling down on the person. And the normal force is coming from the scale, right? Because that's the solid surface that they happen to be standing on. Are there other forces going on? Yes, but not on the person, right? So does the scale feel a force from the floor to hold it up? Yeah, sure, all that stuff. But we don't care, okay? We focused in on the person. Those are the two forces on the person. We're done. So let's go ahead and pick a y direction. As we usually do, I usually pick an x and a y. In this case, don't even need an x because there's nothing happening. And I'll go ahead and do f net y equals may. And we can go ahead and put in what's going on in the y direction. Here We don't need any SOHCAHTOA, of course, because everything's either in the plus y or the minus y. So we have plus normal force and minus gravity. And if you're not doing something like this, like you sometimes do for fun on the scale, just if you're just standing there, what's the acceleration? 0. And so we get a rigorous proof of the obvious that n equals mg. That's something that at this point you probably could have said, why do we just do that? That seemed like an inordinate amount of work to say something we could have just written down. You'll see why I did it in just a second. Now, we've established that the normal force and the force of gravity are one and the same thing. They're going to be the same amount of newtons. So this next question might seem like it's kind of semantics. Does the scale actually measure mg, or does it measure n? What is the readout of your scale actually giving you? It's giving you n, okay? So the scale reading is actually n. Now, how do I know that it's n? It's because n comes from the scale. The scale knows how hard it's pushing on you. The scale is not actually directly involved in the conversation you're having with the Earth, which is the force of gravity. Okay? So the force of gravity is a conversation between you and the Earth, right? It's an A and B conversation, and the scale can see its way out of it, right? So the scale is not involved. The scale actually measures how hard do I need to push up on this person to keep them from smushing me, okay? And that's the readout. So when we say that a scale, quote unquote, weighs you, what we're really saying is that a scale measures the amount of support force it needs to provide to you, which happens to be equal to your weight, which is kind of a mouthful, so we abbreviate it, right? So the scale actually does not directly measure weight. It indirectly measures weight by measuring how hard it needs to hold you up, which happens to be exactly the same as your weight, okay? So it might seem like semantics, because in this scenario, they're the same, but what if I were able to make a situation where n and mg are not the same? Then, of course, we're going to see the scale goes with n, and mg is something different. Now, the way we can do that is by having the acceleration be non-zero. So we can get into this, get this rig in to an elevator with us, okay? So we can have an elevator, and if we have that, let's say, the elevator is accelerating upward, ay is plus. That means the elevator and everything in it, including you, is accelerating upward, right? So if we now look at the forces on the person, how many forces do we have acting on the person now? Still 2, right? Still have the floor pushing up on you, still have gravity pulling down on you, that's it. There's no third force. Net force is not a force, right? It's the combination of whatever forces you have. Sometimes they kill each other, sometimes they don't. Still 2 forces. But if the acceleration is upward, then, if this is the person, the 2 forces can't kill each other anymore. Because if they did, if n cancels mg, you wouldn't be accelerating, but you have to be, because you're inside an elevator that's accelerating. So which force has to win? Which one has to be bigger now? N, right? The upward force has to win, right? If you have a acceleration upward, the net force and acceleration are upward, then the up force has to be bigger than the down force, right? So now n is going to have to be greater than mg. Now, of course, the force of gravity is the same as before. It's just the floor pushes up harder, okay? So this is the same as before, but this is going to be larger. How much larger? Plug it in the equation. Okay? You can see that this equation that we so laboriously wrote down before, what was the point of that? Well, now, instead of the acceleration being 0, the acceleration is not 0. And if you want this to be plus, it means that the plus force has to be bigger than the minus force, and this equation will gladly solve you even. If you just plug in what's the acceleration of the elevator, and you know the mass of the person, right, you can get n. And I'm just telling you what the result's going to be. N is going to have to be bigger than mg. The reason why, again, is because if you want the net force on the person to be up, the up force has to win over the downward force. They can't just kill each other. Okay? So there are several problems in your homework where it asks you to calculate this. It asks you to calculate this in two ways. First, numerical, so and so many newtons. And secondly, as a multiple of the person's weight, mg. So for instance, if you get 1.1 mg, that means that it's 1.1 times what their actual weight is. Right? So those are two different ways to express force. Right? One is as a number, and one is as how many times more than a certain other force. Right? So if you get n equals 1.1 mg, that means that the normal force is 1.1 times their weight, right? Heavier, right? That would be a potential outcome of this, right? So I had a couple questions on what that meant on the homework, because you get two blanks. One is so and so many newtons, the other one is so and so many times mg. So it's a way of expressing a force as a multiple of another force. Anytime that the multiplier is larger than 1, normal force is larger than the weight. If the multiplier is smaller, right, if you get n equals 1.5, or n is 0.5 mg, that means the normal force is half their weight, right? Now, this means that the scale reading, remember the scale reading goes along with the normal force. So your scale reading, this is a way to kind of cleave a difference between n and mg, and I will tell you that n does go, the scale reading does go with the scale, what am I trying to say? The scale reading does change even though your actual weight doesn't, okay? So that's one thing I want to emphasize here, that the scale reading is normal force. You can actually try this if you want. If you have a bathroom scale, an old analog scale is better because it reacts right away. Get into an elevator, and when it accelerates up, you'll see the number go up. Okay? Now, you haven't really gotten heavier. The Earth doesn't really care about you riding elevators. The Earth doesn't pull on you any harder. So your actual weight, mg, is the same as it usually is. But a scale doesn't really measure that. This is the manufacturer recommended usage of a scale, right? This is what you're supposed to be doing when you use a scale. But if you use it in ways that they don't want you to, you can get it to read different things. Okay? Now, I'm also going to tell you something else. Not only does the scale read more than you used to, you also feel heavier. Okay? So this normal force is not only the scale reading, it's also what we call apparent weight. This is to distinguish from actual weight. Actual weight, actual mg, Earth doesn't care. It's always the same. Earth doesn't care about your elevator rides. But how heavy you feel. So believe it or not, how heavy you feel, when you walk around, how heavy you feel has nothing to do with your actual weight. You judge how heavy you feel by how hard the floor pushes up on you. That's how you judge your weight. Your apparent weight, how heavy you feel, is how hard the ground holds you up. Okay? So when you get in that elevator and you suddenly start accelerating upward, the floor is basically trying to come up and smush your feet, right? You have inertia, you want to stay where you are, and the floor is saying, hey, let's accelerate up. But you don't perceive it that way. You think, whoa, I feel heavy. Have you ever gotten in an elevator and you feel heavy? I assure you the Earth didn't just suddenly decide to yank on you just to mess with you, okay? It's the floor is pushing up on you harder than you're used to. And the way you perceive that is by feeling heavier, okay? So distinguishing apparent weight, which is normal force, and also your scale rating from your actual weight, okay? So while it's really just the floor of the elevator trying to come up and smush your feet, you perceive it as feeling heavier. We could do the opposite. Instead of accelerating upwards, let's accelerate downwards. So let's do it the other way. I'll put it down below this one. So let's say that you have an elevator that's accelerating downward, which of course means the net force and acceleration are downward. The elevator and everything in it, including you, has to accelerate downward. So there are still just two forces pushing on you, right? Normal force and gravity. Which one has to win now? Gravity. The down force has to win. So the forces will look like this. mg and n. They're out of balance the other way. Now, mg is the same as it ever is. Okay? Earth doesn't care about your elevator rides. But now the floor is pushing up on you less. The normal force is actually much smaller. It's always the floor, or in this case the scale, which is actually adjusting its push. So now the normal force is less than the scale reading. The imbalance goes the other way. So what do we have? The scale will read a smaller value because the scale reads normal force. You will also feel lighter than you normally do because the floor is not pushing up on you as hard as you're used to. Okay? Has anyone ever experienced this? An elevator accelerates downward, you kind of feel lighter for a second. Okay? Again, it's not really the Earth doing anything different. The force of gravity is the same here, it's the same here, it's the same here. Earth doesn't care about your elevator rides. But the floor is pushing on you differently. Okay? You will feel lighter than you normally do. Let me go and to the absolute, and by the way, if you want to get the number, just plug it in here, right? You just put in your acceleration, right? This will get you the number no matter what. Let's go to an extreme example. I'm going to have an elevator that's not only accelerating downward, like I've been talking about here, but someone cut the cable, the elevator cable, and you're not just accelerating downward at 5 meters per second squared or something reasonable, you're a free fall. Okay? So let's say this is minus g, which is free fall. So what's going to happen here? Well, you're free falling inside a box. Okay? So the elevator's in free fall, you're free falling inside it, right? We learned that gravity treats everything with the same acceleration, right? So instead of a big ball and a small ball that are accelerating together, we have that you are free falling inside the elevator. Now, if this is the scale and this is your feet going like this, how much danger is there of you smushing the thing? None. So how much does the floor have to push up on you to hold you and keep you from smushing it? None. So what's the normal force? 0. It's not just less, it's nothing. So the normal force can go to 0. The scale will read 0, and you will feel weightless. You will have achieved apparent weightlessness. Is the gravity still pulling on you? Sure. It's still pulling on you the same as usual. But the way you perceive it is, hey, I'm just suddenly floating in this box, right? You just don't realize that the floor is accelerating out from underneath your feet as fast as your feet can fall towards it, so that you don't change your distance. You're basically just hovering, okay? Now, you'll get a rude awakening when you hit the bottom of the elevator shaft, right? Then you'll find out it's not that the Earth's gravity suddenly turned off, that you were just in apparent weightlessness, right? And so you might say, okay, this is like fake weightlessness. This is apparent weightlessness where you're just tricking somebody by just pulling out the scale underneath their feet as fast as their feet can fall toward it. You might think, well, this is different from the weightlessness you see like when the astronauts are in the International Space Station, right, kind of floating around. Well, I'm here to tell you it's exactly the same kind of weightlessness. Let's take a look at the quote-unquote weightlessness that they experience up there. It's all apparent weightlessness, okay? So what we have, here is the Earth, here is the International Space Station, here's an astronaut inside it. They can float around for days in there, right? There's no rude awakening at the bottom of the elevator shaft. Here's what's happening. Both the space station and the astronaut are in free fall. And because they're both in free fall, being accelerated the same by the force of gravity, then there's no contact, right? It's the same reason why someone would feel like they're floating if they're inside an elevator that has snapped. By the way, there's an amusement park ride, apparently, where they do the same thing. Have you, anyone been on the drop zone? Okay, so it's like a chair, and then they just let you have a couple seconds of free fall, right? And then they don't let you just hit the ground. That ride is available anywhere, okay? You can jump out the window here and and feel apparently weightless until you hit the ground. At the drop zone, they of course will gently bring you to a stop, right? But what do you feel like when it first cuts? You feel like you're just kind of floating in the seat, right? You're experiencing a state of apparent weightlessness. You feel like your stomach is up here, right? Okay, why is that? Well, everything has inertia, including your innards. So what is it that tells your stomach and whatever that you're going to now do something else? Well, it's the outer part of your body, right? So you suddenly free fall, and then your organs get the message, right? Once they're up here, okay? So what's different from the astronaut in the space station? The force of gravity up there is weaker. Don't get me wrong, it is weaker. We'll learn about that later. But where the space station is, the force of gravity is still 90% of what it is at the surface. So that's still quite a bit. The reason why is because they have apparent weightlessness, because the floor or the walls or ceiling of the space station is not exerting a force because they're falling together. The space station is a constant state of free fall. Now, why doesn't it just come crashing to Earth? Well, it has a little trick up its sleeve. It has a sideways motion. So we learned, of course, if you fire something off in projectile motion, it goes not like this, but it goes like that, right? You can give something a hard enough sideways velocity that it's like, oh, I'm falling, I'm falling, I'm falling. Oh, wait, I'm not actually any closer to the Earth than I was before. You can literally be going so fast to the side that you are constantly free falling and keep missing the Earth. That's what an orbit actually is. An orbit is a state of perpetual free fall. You just happen to have a large enough sideways velocity that you never actually come crashing down. You just keep falling. And then the function that the force of gravity does is it doesn't pull you to Earth, it just keeps you around. Because, of course, by Newton's laws, if you had this velocity and no forces, you would continue to go in a straight line. So you're lucky the force of the gravity is around. It keeps you in a perpetual state of free fall, and it keeps you flying away, but you don't actually come crashing down, because you're in a state of free fall where you keep on missing the Earth. So orbits is what we're going to look at after exam 1. In fact, the very next homework 6, after your exam, is going to be on this topic, at least partially. But I did want to give you a sense. You hear this in the news, you read it online, whatever. No one ever says apparent weightlessness, okay? It's all apparent weightlessness. The force of gravity does not turn off. It's all just the normal force goes to 0. The only way that you can be truly weightless is you go in your little spacesuit, you go out into deep space where you are extremely far away from anything that could be pulling on you. Then you could achieve actual weightlessness, where there's actually no force of gravity that pulls on you. That would be actual true weightlessness. But when you hear in the news, almost inevitably when they say weightless, they mean apparently weightless. It's something that's in a state of free fall with respect to the object that it's in. So a human being is inside something that's free falling the same as the human, and therefore the walls and ceiling don't push on them. Okay? Does that make sense? You can even achieve this on Earth. If you're wondering how NASA trains astronauts to be okay with apparently weightless conditions for days, weeks, months at a time, they have a plane. I forget what the actual name of it, but the nickname of it is the Vomit Comet, because apparently people get extremely nauseous on it. And the way it works is it's a plane. I can't draw a plane, but I'll try. That's about as good as I can do. And what it does is you're basically flying inside the plane, and once you have a certain speed, of course, you would want to undergo some kind of projectile motion based on that speed, right? And what the plane just does is it flies around you, so that, you know, if you shoot out of a cannon, something has to catch you, right? But it's a lot easier if a plane is just flying around you and can make contact at any point to pull you out. So what happens is the plane will actually fly and kind of be a cage around you as you undergo your projectile motion under gravity only. And of course, if the plane's flying around you and doesn't touch you, you're going to feel weightless in there, right? You're not touching any of the ceiling or the floor or the walls, right? You see what I mean, right? The plane is just basically flying around you, and then at some point, it, of course, just gently comes over and catches you out of that flight. That's usually where people get nauseous, by the way, is when it pulls back up.